February 14th, 2011. The Pacific Northwest should have been shaking. Beneath Seattle, Portland, and Vancouver, a section of the Cascadia Subduction Zone was rupturing. The fault moved nearly 2 inches in some places. Energy equivalent to a magnitude 6.8 earthquake was releasing along a rupture zone stretching from Northern California to British Columbia. But nobody felt a thing. This was the quietest earthquake ever recorded, and it was loading the gun for the next big one. Traditional earthquakes happen in seconds. The ground lurches, buildings sway, people dive under desks. But slow slip earthquakes happen over weeks or months. They release the same massive energy, but so gradually that seismometers can't detect them. Your body can't feel them. What makes them terrifying isn't what they do, it's what they're preparing to do. For decades, scientists knew something was wrong with their earthquake models. The Cascadia Subduction Zone runs 600 miles along the Pacific coast. It's where the oceanic Juan de Fuca plate slides beneath the North American plate. This fault is capable of generating magnitude 9 earthquakes and devastating tsunamis. The last one hit in 1700. But the math didn't add up. The plates are converging at about 1.5 inches per year. That motion has to go somewhere. Either the fault releases that energy through earthquakes, or it builds up stress until something catastrophic happens. The problem was that scientists weren't detecting enough small earthquakes to account for all that plate motion. Where was the missing energy going? The answer came from an unexpected source: GPS technology. In the 1990s, researchers installed GPS stations throughout the Pacific Northwest. These stations could measure ground movement down to the millimeter. What they discovered changed everything we thought we knew about earthquakes. The fault wasn't just locked in place, building stress. Deep beneath the surface, sections of it were moving slowly, silently. Here's how it works. The Cascadia Fault has 2 distinct zones. Near the surface, roughly the top 15 miles, the fault is locked solid. The plates are stuck together, unable to slide past each other. This is where stress builds up for the big earthquakes. But deeper down, between 15 and 25 miles beneath the surface, conditions are different. The temperature is higher. The pressure is immense. Most importantly, water and other fluids are present in the fault zone. These fluids act like a lubricant. They allow the fault to slip gradually, releasing energy without the violent rupture that creates earthquake waves. It's like the difference between tearing a piece of paper quickly versus slowly peeling tape off a surface. Think of it this way. The deep fault is like slowly pulling back a slingshot. The energy has to go somewhere. As the deep section slips, it transfers stress upward to the shallow, locked zone. The locked zone can't move, so it accumulates that stress like a spring being compressed. Traditional seismometers miss these events entirely because they're designed to detect rapid ground motion. Slow slip events happen too gradually to register as earthquake waves. The ground might move several inches over the course of months, but it moves so slowly that it's invisible to our earthquake detection systems. The only way scientists can spot them is through GPS stations that continuously monitor their exact position. When a slow slip event occurs, these stations detect a gradual shift in their coordinates. Not the sudden jolt of an earthquake, but a steady drift that continues for weeks or months. The Cascadia Subduction Zone experiences these slow slip events roughly every 14 months. Each one moves the fault several inches and transfers enormous amounts of stress to the shallow, locked zone above. Silent earthquake brings the big one closer. The slow slip event that began in February 2011 was unlike anything scientists had recorded before. It started quietly, as they always do. GPS stations along the coast began detecting subtle shifts in position. A few millimeters here, a centimeter there. To most people, these measurements would seem insignificant, but to researchers monitoring the Cascadia Fault, they signaled something massive was happening beneath their feet. Dr. Herb Dregert from the Geological Survey of Canada was among the first to recognize what was unfolding. His team had been tracking slow slip events in the region since the late 1990s. But this one was different. The geographic scope was unprecedented. From Mendocino County in Northern California all the way to Vancouver Island in British Columbia, the fault was moving. A rupture zone stretching over 600 miles was slipping simultaneously. In earthquake terms, this represented a rupture area larger than the 2004 Sumatra earthquake that killed over 200,000 people. But instead of lasting 10 minutes, this rupture continued for 14 months. The energy release was staggering. Calculations by the Pacific Northwest Seismic Network showed that the 2011 event released energy equivalent to a magnitude 6.8 earthquake. To put that in perspective, a magnitude 6.8 earthquake would cause severe damage across the Pacific Northwest. Buildings would collapse, highways would buckle, thousands of people would be injured or killed. Instead, commuters drove to work, children played in playgrounds. Life continued normally, while one of the most significant seismic events in North American history unfolded beneath the region. The fault moved up to 2 inches in some locations. That might not sound like much, but in geological terms, it's enormous. Most earthquakes involve fault movement measured in centimeters. 2 inches of slip across a 600-mile rupture zone represents a massive redistribution of stress within the Earth's crust. GPS stations recorded the movement in real time. Station ALBH near the Washington coast moved 1.8 inches to the southwest. Station NEAH on the Olympic Peninsula shifted 1.5 inches. Dozens of other stations throughout the region detected similar movements, all pointing in the same direction as the Juan de Fuca Plate's motion beneath North America. What made this event particularly alarming was its location. The 2011 slow slip occurred in the transition zone between the deep seismic part of the fault and the shallow locked zone that generates major earthquakes and tsunamis. Think of the fault like a loaded spring. The 2011 event was like slowly compressing that spring even further. All the energy that slipped silently in the deep fault didn't disappear. It transferred upward, adding stress to the already locked, shallow fault. Researchers at the University of Washington calculated that the 2011 event increased stress on the shallow fault by approximately 1 to 2 bars. That might seem small, but it's equivalent to adding the weight of the atmosphere to an already critically stressed system. The timing was also significant. Cascadia's last major earthquake occurred in January 1700. Geological evidence suggests these great earthquakes happen roughly every 300 to 600 years. We're now 324 years into that cycle. The 2011 slow slip event essentially moved the fault closer to failure. It loaded additional stress onto the shallow zone that will eventually rupture in the next Great Cascadia earthquake. When that happens, the resulting magnitude 9 earthquake will generate tsunami waves that could reach heights of 100 feet along parts of the coast. Current monitoring shows the fault remains under extreme stress. The locked zone hasn't released any significant energy since 1700. Meanwhile, slow slip events continue to occur every 14 to 16 months, each one adding more stress to the system. The most recent major slow slip event occurred in 2016 again. Spanning much of the Cascadia zone, smaller events have been detected regularly since then. Each one represents another increment of stress transfer, another step toward the inevitable major rupture. What's particularly concerning is that similar slow slip events have preceded major earthquakes in other parts of the world. Before the 2011 magnitude 9 Tohoku earthquake in Japan, researchers detected increased slow slip activity along the fault. The same pattern appeared before large earthquakes in Mexico and Chile. The correlation isn't perfect, and slow slip events don't always lead to immediate major earthquakes. But they do indicate that the fault system is becoming increasingly unstable. The silent earthquakes aren't just scientific curiosities, they're warnings. Every slow slip event brings the Pacific Northwest closer to a catastrophic earthquake. The Cascadia Subduction Zone hasn't produced a major earthquake since 1700, but geological evidence shows it's capable of generating magnitude 9 events that would devastate the region. The stress from slow slip events accumulates on the shallow, locked portion of the fault. This is the most dangerous part of the system because it's where tsunami-generating earthquakes originate. When this zone finally ruptures, it will happen violently and without warning. Unlike the gradual movement of slow slip events, the next great Cascadia earthquake will occur in minutes. The fault will rupture along its entire length, generating ground shaking that will last up to 5 minutes. Coastal areas will experience tsunami waves, arriving within 15 to 30 minutes of the earthquake. The invisible nature of slow slip events makes them more dangerous than earthquakes you can feel. When a magnitude 5 earthquake rattles dishes, people remember to check their emergency supplies. When a slow slip event transfers equivalent energy to the fault system, nobody notices. This creates a false sense of security. The Pacific Northwest has experienced relatively few large earthquakes in recorded history, leading many residents to underestimate the seismic risk. Meanwhile, slow slip events continue to load stress onto the fault system, bringing the region closer to a major disaster. Scientists can't predict exactly when the next great Cascadia earthquake will occur, but they can monitor the warning signs. Slow slip events are one of those signs. Each event represents another increment of stress added to an already dangerous system. The frequency of these events appears to be increasing. Historical data suggests slow slip events have become more common in recent decades, though this could be due to improved monitoring rather than actual changes in fault behavior. What's clear is that the fault system is becoming increasingly unstable, and the next major earthquake could happen at any time. The quietest earthquakes are loading the gun for the loudest one. While slow slip events happen silently beneath our feet, they're preparing the Cascadia Fault for a magnitude 9 earthquake that will reshape the Pacific Northwest. Download earthquake early warning apps and prepare emergency kits now. Subscribe for more hidden geological threats.